Would you rather have like a standard shot or?
Nah, this is fine.
Okay.
It's mostly just capture the audio, then I'll post the post later. All right. So for those of you who are sticking around, welcome. For those of you who are still talking to your teams, continue to talk. I'll just talk very loudly. We're not going to try to stop CougSat-I. Well, again, if you're not familiar with me, I'm Colin. Been part of Cubesats Space for the last 4.5 years. It goes by really, really fast. And today, I'm going to be talking through a presentation I'll actually be giving in a couple of weeks to this really small company in Los Angeles called SpaceX for a position I'll be interviewing for them. So I figured as part of it, because they kind of want me to talk about my experience developing satellites, I usually do a little practice run, so I figured it'd be helpful to do the practice run in front of you guys, in addition to me actually getting the practice. Maybe you guys learn something along the way, and then see kind of how it all started out, and you guys can get ideas for CougSat-II. So, this is how to build a satellite, specifically the hardware, in a school that doesn't have an aerospace program from scratch. I will skip these next two slides, because this is more stuff they want to know about me, like, okay, that's my face, this is what got me into it. Here are some other projects that I worked on. Most of you from Payload team are probably familiar with it. I published research. Yeet. Cool. Let's get to the fun stuff. So, CougSat-I, stuff we're working on. What was the initial thing that we set out to do? So, it kind of changed and morphed in a bunch of different ways. As you can see from a few of these guys here that have these beautiful depreciated logos on it. But the main objectives, the first main objective, because it was our first satellite ever, was to develop a reliable and robust satellite bus system, which basically means can we set a satellite up and make it work. There's a great paper called The First 100 Cubesats that actually did an analysis on Cubesats and how often they succeed or fail, which groups tend to succeed and fail. And they tend to fail for groups at about a 50% rate. So that's very inspirational news for all of us. In terms of, okay, success or not success. So for this one, to see if can we put something up, make it successful. We had the even more ambitious achievement, probably because of a certain Mr. Davis over there, to make a lot of our electrical power systems, avionics, magnet torquers, comm boards, all from scratch. Typically, a lot of teams actually will buy them off the shelf, so this is already really ambitious in and of itself. Initially, when we did CougSat-I, now I'll talk a little bit about some of the stuff that was taken off, but maybe you guys want to toy with the idea for CougSat-II. In addition to the germination chamber, this actually came along 6 months into our life cycle design because we actually had one of the top astrobiologists come by who was staying at the school, Dr. Ashvin Khan, teaching here. She actually came up with a design idea, so we put together compile a germination chamber for her idea for growing seeds in space. Some other things that we did, we had an idea of reprogramming the boards from the ground, computing systems that might be a little bit much to bite off, so we removed that feature. But that was an initial idea. And then a couple other things too is we actually had a laser on the bottom, camera on the bottom. To my knowledge, those are both not there currently because we're trying to scale it back, make something that works. And finally, one very fun thing I was kind of disappointed we didn't get working, or we didn't actually end up pursuing because we ended up having this germination chamber. So we actually had a little bit deployable Cougar head. So you had the camera right there, and then the Cougar will be inside of here, and then the Cougar head will get extended out, and then you could take pictures of Earth with the camera, and you have the logo there. You get a lot of clout from all the alumni. But that ended up being a little bit more involved, especially when you had the requirements creep that you did for the first, you had a germination chamber, you're making everything from scratch. So one lesson that was learned is when you're making a mission, stick to one, possibly two payloads, and don't try to invent the whole wheel from scratch as much as possible, because it's going to be a lot to chew. So that's CougSat-I, a little bit of the overview of all the systems. Something that you guys will have a fun time doing, and I will briefly touch on it, because it is very boring, but it's very necessary. It's something called the Design Requirement Sheet. So each team, if some of you want to go to the Google Docs, have a beautiful thing that looks like this that tells you all the things that your specific subsystem needs to do. Each one of these line items is very particularly worded because each one of these line items, if it's on here, actually means that there's going to be hundreds, hundreds of hours of engineering time, thousands of dollars to spend. So when we go over the design requirements to actually write them, I still fondly remember talking with some of the people at Lockheed who was helping us review and create one of these. Each one of these lines, you could spend anywhere from 15 minutes to multiple hours talking about it, because if you include this line, if you can save yourself from, if you can not include the line, that saves yourself a lot of time. So there's a lot of thought that goes into, okay, does this requirement actually need to be here? Needing fasteners or heat sink and radiation sink. You really spend a lot of time thinking about what your specific subsystem needs to do. So yeah, there's a little bit about those different ones. Basically, all these, for the structure side is you need to keep all the deployables stowed away until they deployed. A few things about thermal requirements. The structure shall be a structure, which seems redundant, but you have to put this in the design requirements, which makes it very, very dry reading at times. There you go. That's what we start out with for the design requirements. And if you actually, as I'm talking, if you have questions or just want to yell out random shit halfway through the talk, feel free to. This is mostly a monologue, but some of you guys, I'm trying to teach the lessons learned. So if there's something you don't quite understand, or you think might be important for CougSat-2, feel free to interject at any time. Another thing you do, so you have the design requirements. One thing you tend to do a lot for the hardware side is you do a preliminary design review. And one of the things you do for part of that is, you come up with the initial design, you say this is where the rough CAD model, usually come up with a general idea. Something you look at is the risk analysis. So each subsystem typically goes through this process, structures. There's a few things that we looked at, became more involved or less involved depending on how the system requirements changed or how the mission developed. Some of the things we looked at, again, because you have the structure itself, you have to worry about, bolts. Are they going to basically yield or break? Are they going to twist out? Is the aluminum going to break? Because for certain random vibration environments, maybe there's a big moment arm as it's randomly vibrating. To worry about that. A couple of things about separation springs and switches. The thing we're launching out of, it's going to open up. You want the thing to eject out. That might be a concern for that. So you have to include that there for your risk analysis. And this is, of course, a first pass. As you develop the thing, you may find up other things that come up on this. But yeah, you say the risk, describe what it is, what your first pass likelihood estimation is of it happening, and then you come up with a plan for how you're going to mitigate it, which in the case of the hardware is mostly random vibration tests, which if you're not familiar, we'll talk a little bit more about that later. But it's basically just shaking the satellite really, really hard and see if it breaks. So that's how you check to see if most of these things are compliant or not compliant. So, awesome. We have the very dry design requirements, and then we have the risk analysis. Now we can get into the fun stuff. So, as a first year freshman, you'll have my story about, I come in, music major, transition to mechanical engineering, couldn't tell you the difference between a bolt and a screw or what a threaded rod is. So I figured, let's get some hands-on experience and see how you would actually go about putting this together. So the first project I jumped into was designing and manufacturing a chamber, or basically a 1U CubeSat for the thermal team. The thermal team had access at the time to a thermal vacuum bake-out chamber, and because they were super new, they're doing a lot of hand calculations, but they're not sure if their hand calculations are correct. So it's nice to have some hardware for them to see if it's actually, their rudimentary calculations work out or not. So this was the first satellite we created. This was all water jet, machined, and CNC'd in the Fizz. We didn't go hire some third-party things. This was literally all created there. As you can see from some of the very simple geometries there. The side panels here, all water jetted. The panels, top and the bottom ones here, those are actually using the CNC routers, funny enough, available in the Fizz. Because, contrary to what they have you believe, a lot of the ones that can do wood, if you run them slowly enough, can also do aluminum.
Look at he said that. He didn't say that.
Just don't do it in the wood shop, or if you do take the thing out. But yeah, that's how, this panel, for instance, this was something I actually had to convince Greg, who was my team lead at the time, that some of these machines were actually viable ways of machining it. So, this was a proof of concept. So we machined that, the top and bottom plate, hand drilled out the holes here, and then, you can actually see it in the room today. The tolerancing was pretty good. If you look at it closely, if you actually pick it up, you'll notice it's slightly tilted. That's primarily because these holes being hand drilled, I didn't actually have a movable rail to actually physically displace. Okay, this hole's going to be exactly 3 millimeters to the left plus or minus 0.1. I literally just went, okay, I'm going to draw a little dot, and then I'll just literally grab it by my hands and then just kind of drill a few holes until it all lines up, as you may see if you look at it closely enough. But cool, that was the first thing we did. This is a great experience, especially if you guys are starting out. If you can go through the process of building 1U aluminum sat just to get an intuition for the different CNC, water jet manufacturing processes, this is a great first project to jump into, especially because you don't need to know GT, you just need to know how to drill holes, do some chemistry. So cool, all right. The construction team now has some experience building some hardware. So this jumped into our first project, which was CubeSat-I. This was our first attempt at building a 1U, actually 3U, 1U specifically being metal, and 2U being 3D printed. This was our first attempt at seeing if we could actually make this satellite. Because a lot of us, we hadn't made one before, hadn't gone through the process, so this was our, okay, let's see if we can actually make one specifically for the Aerospace Club. Back in 2018, they actually made this really cool rocket, which actually had like a differential diameter nose cone, and then actually concave down to a different body tube. And as part of the, basically it's known as the IREC international competition, they actually had a deployable spring where they could actually put in a 3U CubeSat. But at the time, they were looking at making the CubeSat in-house. No one was doing it within the team, so I decided, okay, let's get some people from structures to actually go and make the 3U here. So I'll just briefly talk about this 1U. Is actually one of the first revisions for the structure that we're still, unfortunately, working on today. The primary thing was to determine, I'm not sure if you can see it from here, we had some really thin rails we weren't sure that could be machined. So this project was to see if we could actually machine those rails to hold the board. Successfully did that. Right here, we actually have a 2U, all 3D printed, something that's a little bit easier to manufacture with just water jets and a couple of CNCs. And then in between, we actually had a threaded rod that went in and connected both of these together, and then a parachute just in case we did decide to deploy it. Some GPSs as redundant backup just in case we lost a rocket, which we'll circle back to in just a minute. And yeah, that's how it all came together. One other thing we want to check too is, okay, could some of the boards that we designed, could that survive the acceleration environment? So that was the first prototype. See if we could manufacture it. We were able to. Mad brownie points there. And some of you could be asking, cool, okay, so you put it in the rocket, you launched it, how'd that go? Well, we never got it back. It went up, and it started going over, and then at that point, you expect some parachutes to deploy. We saw the black powder go off, but we didn't see any nice big orange bright blob in the sky going off. We saw a nice little thing starting to hit terminal velocity at about 10,000 feet and go straight into the ground. So that was a very sad day. We were hoping, okay, some of the GPS things on there, they had SIM cards in there, and they can survive some pretty high G forces. Maybe those survived. Turns out we were in the middle of the Mojave Desert, and there is no cell phone service out there. So yeah, those were, even though we have 3 of them, they're 3 completely dependent. They're all dependent on one point of failure. So if you learn anything else, if you're going to have redundant systems, make sure they're not all redundant on the same common point of failure. But this is what she looked like. We had originally 3D printed it, prototyped it here. Actually, our old mentor, Crandall, actually did all the electronics for it, which was a really fun project. It came together over here. Now she's stuck somewhere out in the New Mexico desert. Cried about her to this day. But yeah, that was our first pass at making a 1U, and at least we got that out of the way and actually got some experience integrating a CubeSat into a rocket, even though that rocket only went to 10,000 feet. It's still starting. So cool, we got that experience. Now we can actually start going about developing the flight hardware for CubeSat-I. You have some experience with that. So, what did the design process look like? And I know Structure's seen you guys already doing this, so you guys are kind of old news. But the initial thing, because we weren't sure where to start, is we decided, okay, well, we have this great 3D printing technology. We're going to go ahead, start designing it, and we'll just do rapid iteration and testing with 3D printed models. And then you can do basic fit checks to see, okay, are these holes lining up roughly? It's easier to work with things if you know, okay, I have this 3D printed model, let's put the batteries in there. Okay, it looks like actually, it matches up our CAD, that's nice. This is a great one, actually, a certain Aiden Pyle a couple of years ago did. It's part of structures where this is actually all 3D printed, even the components, which was incredibly well done. So I wanted to feature here and give him some props to that. This, of course, is the satellite that we've machined and hard anodized today that will likely go up to space. So we have actually the components on there, RF board, and then all the other things that get machined around. Of course, the germination chamber, that was actually machined out down here. So that's coming together really well from the payload team. And then we actually had this really fun component because we actually had to manufacture the removing for flight pin, which I think sticks out. It's kind of hard to see from this picture even for me. Will stick out, I think, somewhere on this side. But you need some pin to be able to hold it in there. And because it was such a weird, it wasn't the most friendly to machine geometry, we actually ended up 3D printing it actually out of Dr. Amit's lab out of titanium. It actually came out pretty well. Then, in addition to that, and they weren't, they're expensive, but not expensive compared to some of the other things that could 3D print. Once that goes up into space, this is something we can say, hey, Dr. Amit's lab, you guys work on a lot of rocket stuff, and a lot of their work is super relevant for aerospace. Now they actually have a component up made of titanium, actually helping out with the satellite. So that's pretty cool. But yeah, that's the CubeSat-1 flight hardware. Talk a little bit about the fun engineering drawings we put together. Won't go into too much detail, but one of the things, funny enough, that even as a mechanical engineer that they don't teach you enough about, that you actually spend 90% of your time doing, is this thing called GD&T. It is incredibly boring, and I'm not going to bore you with all the details about what goes into it. But the end result is that you get to have some beautiful drawings that look very professional, and you can put them on your resume, and they go, wow, you should be a mechanical engineer for us. This is all comes together for that. Kind of the process that we go about for doing that is you go actually talk to the machinists, you create the engineering drawings, you go back and forth with them until they understand, okay, this feature, how big does it need to be? How does this interface all together? One lesson that we learned, maybe we'll have a little debate about this on the spot here, but the method that we determined to hold the EPS or all the different electronic boards was to have these little 1.8 millimeter slots milled out that they could slide into, and you had two of them on both sides, so you can kind of clamp them together, and they all fit nicely. The problem is with these is that these are fairly expensive to machine because those bits are 1.8 millimeters. If you know anything about feeds and speeds, you have to run those really slowly. And when you have machinists that are getting paid $80 an hour, and you have when you're doing this for you haven't done slot sizes like this before, you get fairly expensive when you do non-standard bit sizes like that. Really long, really small, thin rails. So this was something where kind of a lesson learned that we would suggest you guys do, or I guess steer clear of, is that you need to have a way to hold all of the electronic boards together. This is one way, but what we found, machining, this ended up costing about $3,000 to $4,000 to machine. Most of it was because of these features here that we had to machine away. There's a much easier way to do it, which basically involves taking 4 threaded rods and putting standoffs in between, and literally all you have to do there is just drill holes. That's it. You don't have to worry about any of this stuff. We'll probably have maybe a better example towards the end of the talk. But yeah, that was some of the engineering drawings we put together for that. Avoid from the lessons. And here's one other fun one we had. So again, because we were making this satellite back in 2017, we didn't know who was actually launching us. So we had to go off of the Cal Poly CubeSat design document for all of our requirements, and they said, okay, you need certain deployment switches, you have all those requirements. Cool, so we had made this first panel for them and to meet those requirements. Well, we find out later, we have this great little launch service provider called NanoRacks. And they're nice, they're a young startup, helping out, great energy. They had this weird little thing that didn't quite match up with the old Cal Poly requirement, where instead of one physical deployment switch, where basically if you push it down, it disables all the electronics, and then when it gets released from the thing that's holding it, cool, all your electronics can turn on. They needed 3 of them. And if I remember right, you can correct me if I'm wrong, Ryan, but they didn't actually put that requirement physically in their document. They kind of told us about it, and then we went, we don't see this anywhere in your thing, and they went, oh, we forgot to include it. So we had the fun, unenviable job of taking this thing that was already machined and spending multiple thousands of dollars and having to work around it and make basically, a few drilled holes, slots, so we could fit those 3 deployment switches in a CubeSat that was already very much volumetric constrained. I even actually, Tony and myself a couple of days ago are still having to work at this to this point, because now it looks like, even with this one design that we can make work out, it sounds like it's running into some of the attitude stuff. So it's just an overall nightmare. So the lesson that you can learn here, if anything, if you can, find out your launch service provider as early as possible, because if that stuff changes, sometimes requirements can change. And going back to the earlier conversation, if your requirements change, then your hardware has to change, and that ends up costing lots of money because then you have to do another operation like that. So that was another fun lesson learned. All right. So this part's a little bit more, I guess, esoteric. This whole testing sequence you don't really need to do, especially for our systems. But this is just a generally good process to do. And if you could say you've done bulk torque testing, which is 3 words to get anybody really excited. This is something that you can, that's actually a good process to go through, because you can actually understand, okay, the thing that's actually holding the satellite together, you can actually codify the failure modes of bolts and stuff like that. So back in, I think it was like 2018, with the very first team lead, Greg Wallace, one thing he wanted to look at is, okay, we're looking at M3 bolts, but we're doing some analysis, okay, how much do we need to twist them in to hold the bolts in place? Because if you actually over torque them, the bolts will actually, they will over twist, and they actually won't grip the threads that need to go into. So you have this weird balancing act where you need to twist them enough that they actually hold down to their maximum force, but you don't over twist them such that they just start spinning and then they just don't grip. So this technique that you do is called bulk torque testing. A quick little picture of it. For those of you who've done ME220, this is a little tensile testing, little holder adapter that we made. On the bottom here, you actually put one of the 1/4-inch bolts that adapts to the bottom of the load cell. The top part, there's another adapter. In the middle of that, you actually put the M3 rods that you're working with here. There's a little hole there. And you can actually pull it until either the bolt breaks or it actually will slip in the threads that's holding it together. So we checked a few different things. We checked the conversation about different bolt configurations. We checked socket heads, which are basically the standard ones. They have these nice little extruded heads that are pretty easy to interface. Button head cap screws, that was the other one we checked. We needed some more low profile bolts to work with, so we wanted to see, did those ones slip at earlier forces? And then we actually tried taking these 2 bolts and threading it into 3 different things. 2 of them were nuts, because that was a common way of actually mounting them. And then one was actually a piece of aluminum that we had water jet out and then threaded into, and then see, okay, given that we have a lot of aluminum threaded connections, is that going to fail at an earlier point? So here's some of the results from that really quick, just to briefly talk about. Again, these are all alloy steel socket heads, but it's going back to the socket head versus the button head screws. What we found is that the socket head, which, just to remind you, looks like this guy down here, these guys tended to be able to survive the highest forces without actually breaking their threads. At least breaking their threads when they had a nut at the end of them. They were able to stand about 1,000 megapascals force. Took a few trials, and that was about the range they could do that. From down there, as you reduced, basically you got lower profile bolts. You actually got this. You started to see the bolts started to strip at earlier forces. So you got to see, okay, instead of 1,000, we're revolving around 750, going to the nuts. And the final one, this was actually, interestingly enough, the connection that we saw the most, was the socket head cap screw bolts threaded into aluminum. We were only able to take one because the parts that we machined out on the water jet, we machined them out to be about 1/4 inch on each side. And funny enough, after you water jet the part, it will actually fall out of the thing that's holding it, and then it will go to the bottom of the water jet. So we had machined 10 of them out, and we were like, okay, we'll just fish them out. And after all the fishing, we were only able to find one after 30 minutes. So ideally, you would take more data points and have a better water jet setup where you actually have a little,
Edge.
Yeah, a little edge. You can, break it off instead of cutting all the way through. But well, lessons learned. We got one data point. As you can see here, if you thread into aluminum instead of stainless steel nuts, you have a much lower failing force down here. So yeah, this is the number that we're actually going to base some of the calculations to see on the next slide off of. That's the one we'll go off of there. Go to the next slide. Actually, just kind of quickly talk about, because interesting little, I guess it gives you a nice time lapse of what happens here. When you actually have the bolts in the threads here, and then as you're pulling it, it actually doesn't pop out right away. You'll see it, it'll apply a force, and it will be, the force will go up as the strain on the bolt increases. And then at a certain point, because it's threaded, the threads will actually kind of, they'll jump a bit. So you'll see it go up, and then it will kind of skip within the thread. So the thing will pull up, the threads will actually jump a bit, and then some of the threads will actually catch, and then you get that same sequence again, kind of going up here. So if we follow, let's say, this red line, you're pulling, and then the threads unstrip and then catch again, and then you have that pattern kind of going all the way down until the bolt basically falls all the way out. So it's not a clean break right away. It actually takes a few iterations, but yeah, little interesting chart there. In case you ever really wanted to get into real deep details, or just wanted some pretty pictures there. To quickly talk about the calculations, as I know we all really love math in this place. I'll just briefly talk about them. You have a bolt. Okay, we did the calculation to determine, okay, at what force when you're pulling the bolt out, will it strip its threads? We found the lowest one was about 450 megapascals, so that goes into the equation. We're working with M3 bolts. Okay, so that's going to go up there. Pitch, of course, with what we're using M3, half a millimeter pitch. From there, you can calculate the slip area from this equation, which is derived like the tensile stress area, and you can Google all this stuff. I would just look at the slides because I'm not going to bore you with the details. But okay, you can determine the area in which that stress is actually applied over, and then okay, that stress times the area, you get the force that induced the slip. Then from there, you can apply what's known as a nut factor, which is basically a little correction factor to compensate for whether the bolt is actually lubricated or not. If you have a bolt that's lubricated, the threads from the bolt will actually grip the threads of the female end is going into, so it will hold a little bit longer. So you have a little correction factor there to compensate for that. And from there, you can calculate from all these previous equations for your torque wrench, what torque do you need to put that at in order to get the maximum torque out of it without stripping the bolts. So we actually did all the calculations, and of course with calculations, you like to check them. This is the results, or at least videos of the results. I tried to actually go find the original data, and after multiple hours of digging, I could not find the data. The nice thing is, we actually mentioned some of the previous results that we got in one of the videos we have on the CougSats in Space channel. And one of those data points was that for some of our unlubricated we're making up new words as we speak, bolts, we found that they tended to fail around 13 pound-inches unlubricated, which if we go back here, unlubricated joints tend to have a nut factor around 0.1. So if you do the calculations there, or 0.19, you do the calculations there, we calculated, it would strip around a torque of around 12 pound-inches. Experimentally, we found it did it around 13 pound-inches, so it was nice to see that they actually matched up. But in terms of, for structures team, if you guys are using that torque wrench, what do you torque it to? You would likely do it around 10 pound-inches, just to add a little factor of safety there. So, bolt torquing, whoa, really exciting stuff, but still necessary. Finally, we'll talk about the final thing, which I kind of mentioned before, vibration testing. If you need to say nothing else from your interviews, what this is nothing more than a fancy way of shaking your hardware and then seeing what breaks. You usually have to base, there are certain profiles that you can base your standards off of, or that determine, what loads you need to put into your different vibration tests. Ours was this one from the Goddard Space Flight Center initially, because we didn't have the launch service provider, so this is an industry standard one to use until you find out from your launch service provider what actual loads that you're subject to. Then we found out, NanoRacks was our provider. They have this nice little chart down here, which is basically, for those of you who aren't familiar with an acceleration spectral density spectrum, which is another exciting set of 3 words, is nothing more than, you can think of it as the equalizer of the kind of your input load. So, if you have, let's say, music, and you're putting out a sound, you can boost the low end, so you can get, you can make your car really bump. Or if you're like, I don't know, I'm listening to classical music, you can turn down the low end and turn up the treble because you really want to hear those piccolos. Vibration testing has the exact same analog here, where there's certain lower frequencies on your rocket that might be, at certain levels, and then as you go up, there's more prominent load levels in like the 200 and higher ranges. So you actually have to put in a profile much like the equalizer in your car audio system that actually gets put into your shaker system. It gets inputted onto a vibration table, which is basically a fancy speaker. In fact, if you plug in, as we have one of our setups for 406, because we're currently going through the testing, you could actually plug in an audio jack, and you can put it in your phone, and you can play your favorite Katy Perry song. And you can see, does your board survive Katy Perry at 2 decibels? So that's pretty fun. I don't know if you want to do that testing, but it gives you some mad fun. So that's awesome. One other thing we talked about too, because in terms of random vibration testing, go back and briefly talk about it. How you mount your hardware is very important. So for instance, our boards are held together by 2 rails. So when you're doing the vibration testing, you want to make sure that when you test it, it is held in a very similar fashion to how it will be held in the launch environment. So actually, we have one of the engineers here who actually came up with the design for clamping this thing down, made out of 3D printed PLA right here. But yeah, clamps it down in a very similar fashion to the rails. You actually shake it, and then the forces that this thing will see here will be very similar. This is what's known as kind of a sub-level, a subsystem component test. So we're actually testing the boards individually. The one test you want to do is usually, okay, you want to have the actual satellite, vibrate it, put it on the table. So you actually have to come up typically with a fixturing system to mount the satellite to the table. So this is one we came in-house, or developed in-house, ended up costing about $1,000, which is actually cheaper than buying one, actually renting one for that matter. But yeah, this is all made out of aluminum. Yeah, it mounts right here. You can see on the side of it, there is the one Cubesat that we have here. Around it is the actual housing that sits in it. So what you would do is, okay, you put your Cubesat in, you close the plate. There's these 5 bolt hole patterns over here that would interface between the fixture and your actual vibration table. So it's not pictured here, but the vibration table would actually have a big board of, like say 20 by 20 rolls of holes. And then you would take your fixture plate, screw it to that, and that's how you're able to actually take your satellite and put it on the table and vibration test it that way. So there you go. And you can actually get, if you know that much, you can actually get whole people going out and trying to recruit you because you know vibration testing. Because it's one of those things that is not sexy, but every company needs to do it. So there's that. I guess one brief thing. Of course, it's nice to have hardware you can test, but of course, doing it in simulation is always nice. SolidWorks, of course, has the ability to do linear random excitation, random vibration excitation. So this was some of the initial results we did back in, I think it was in 2018. YouTube video we threw together just about, okay, how does the process go about setting up? I guess some people end up actually liking it, and I think we actually got a comment the other day about there's some kid working on like a moon interface bracket to actually use this tutorial. So I don't know, if you want to learn how to do it, I guess that's helpful. But yeah, basically you do it in SolidWorks. You see, okay, in our case for the 406 project, we're putting our PCB in, we get a certain, okay, we know these certain loads are coming out, it'll have this certain stress. You can actually put accelerometers on here and you can determine, oh, okay, for this accelerometer, is this actually matching up the simulations? If it is, great. If not, go back and tweak your simulations until it does. And that's a nice little thing to, if you know your simulations are matching up your actual tests, you don't have to shake your hardware as much, which can always cause problems for failure, because if you test your hardware too much, then guess what? It doesn't pass the actual test. Much like a undergraduate student when you overtest them. Too many of those. So there you go. That was the whole CougSat-I. You got full circle again. Started with a thermal model. Made a 3U for the aerospace club, which is actually likely a project that you guys would do, and I highly encourage you because it gives you a good idea of what the iteration cycle looks like for how you develop a satellite, how does the launch go, and then mission success or failure. You can do that within a we're working on 3 to 4 years for this satellite. That project takes a year. You get the experience really fast, and you can take those lessons learned right away. Go from that to bolt torque testing, which if you guys want to go through that process again, cool, you have that. But I would say at this point, you can just kind of go through some of the calculations and some of the formula calculators we put together, and that should keep you set. And honestly, in terms of failure for CubeSats, they end up only failing around hardware like 8% of the time. And there are middle schools who are putting these things together. So there's you wouldn't necessarily need to go through the bolt torquing calculations because a lot of them just kind of screw them in with some thread lock and go, all right, that seems good enough, and it tends to work most of the time. But if you want to get into the really hard details, you can do that and talk about random vibration. So we'll talk a little bit about what's looking forward for CougSat-2. Now that we have some lessons learned, we can pass it off to you guys to go carry on the future of the club and make us 6 U's and 12 U's and I don't know, make new U's with 3 numbers in it and all that fun stuff. So the first thing, of course, we talked a little bit about before, as part of the process that actually got us the CougSat-1 launch. This was all thanks to a NASA CubeSat launch initiative proposal. If it wasn't for that proposal back when Crandall, our first advisor, made it, this whole club would not be here. So the first process is putting together a great 20 to 40 page document of talking about what the club did, what you're planning to do, getting people from industry to kind of vet it over and give you feedback. So we were able to go through that, got that done. And so this is what we proposed to NASA. Again, we made it broad enough that if you guys need to, because you guys are the ones taking over, have to scale back some of the ambition that's being put forward in CougSat-2. You have that available. But the thing that we're looking for CougSat-2 is, well, we have CougSat-1. We did CougSat-1. We see what systems were successful or not successful on CougSat-1, and then you can take, you have now you have another 3 years to continue to develop those subsystems for CougSat-2. And then in addition to that, a couple things we're looking at is putting on a propulsion system. The small, quote-unquote, easier one to get to is a cold gas system. That's literally nothing more than like a CO2 canister and a valve. You just open and close that. And you think that would be pretty straightforward, but like if anything in space, there's always 200 pages of documentation that need to go along with that to show you're not going to hurt the spacecraft. Maybe not that much, but I guess you guys would have line up the fun way. And then, of course, the stretch goal is, okay, if we can make the cold gas system work, you can actually get a little bit more performance or a bit higher thrust out of it by putting an electric thruster at the very end of that gas. One thing that the payload team's looking at right now is actually a Hall effect thruster, so they could talk away about all the fun intricacies that go into that. But yeah, that's what we're looking at for CougSat-1 or CougSat-2, CougSat-1 plus 1, I guess. Looking at kind of the overall number of people that we've been able to do. 400 students have gone through this program in the last 4 years. I think there's been a few thousand views online from our different websites and channels and stuff like that. It's been an incredible ride. Don't have really anything eloquent to say other than it's been fun. Thank you, Wazoo, and everybody else for having me here for 4.5 years, and hopefully you guys can be up here in 1 to 2 or 3 years, giving your monologue to a group of mostly interested and maybe some people taking naps in the back students on what you were able to achieve. So yeah, thank you. Any questions, I guess? Or hand clap, I guess. That was just awesome. All right, you guys are free. Yeah, you can get my microphone. This is going to help you. You need help recording the thing.
Yes.
Yeah.
Hopefully it doesn't take more than 5 attempts.
Oh God,
This is for your interview process?